we have been discussing about Grashof criterion and the presence of a completely rotatable link in a kinematic chain. We have looked at the 4R chain. So, today we are going to go further in this discussion. So, here is the overview of today's lecture. First, I will show you how a 4R chain can be converted to a 3R 1P chain. This is called metamorphosis, a gradual change of a 4R chain to a 3R 1P chain. And then I can extend the Grashof criterion for the 4R chain to various other chains, as I will show you in this lecture. Then we will talk of inversions and assembly modes. So, just to review what we have already discussed, we were looking for a completely rotatable link, because in many applications you have a rotary motor driving the input link. So, we look for presence of crank. Crank is a link that can rotate completely and hinged with the ground, and the motor is fixed to the ground. So, we are looking at the presence of crank in a kinematic chain. We have looked at these examples, the 4R chain, and today we are going to look at this 3R 1P chain, which I have shown here. Just to review the discussions we had on Grashof criterion. If L min is the length of the shortest link, L max is the length of the longest link, and P and Q are the lengths of the intermediate links, then Grashof criterion says that if L min plus L max is less than or equal to P plus Q, then the shortest link can rotate completely with respect to all other links. So, this was essentially the Grashof criterion for 4R chain, and we say a 4R chain to be a Grashof 4R chain if it satisfies this Grashof criterion. Now, let us come to this, what I call metamorphosis, from a 4R chain to a 3R 1P chain. So, I have shown all the stages in one go. So, here we start with a 4R chain, which I can think of as, so this link I can think of as a curved slider rotating on a sliding surface whose radius of curvature is same as the length of this link. So, the length of this link is equal to the radius of curvature of this path on which the slider is moving. So, essentially it is the radius of curvature of this pin. So, it is the radius of curvature of this pin, path of this pin, because this pin is going to have the same radius of curvature L. So, I can put it on a slider such that the pin describes a circular trajectory, circular path with this point as its center. Now, I start taking this further and further till it goes to infinity. So, I start taking this ground hinge down further and further till this goes to infinity. So, which means the radius of curvature is going to infinity. So, curvature becomes 0. So, this becomes a straight path. The path of this pin now becomes straight. So, this I call metamorphosis of a 4R chain to a 3R1P chain. So, this is R, there is one R here and a P here. Now, here I have a definition. You see that there are these link lengths. So, one is this length L, and let me call this as L prime. So, L is this link length and L prime. So, this is L, I have marked it, and this is L prime. Now, as I take this hinge to infinity, this L goes to infinity. And what is L prime? L prime connects this hinge to this hinge. So, that also goes to infinity. But then, if I look at their difference, imagine that infinity is actually a very large number. If I look at their difference, the difference is exactly this, which I call E. The difference in these two infinities is E. E is known as the offset. The offset of a 3R1P chain, E is known as the offset. So, offset is the difference between the two infinities, two link lengths that are now infinity, and you can see that one is definitely larger than the other, and this difference is the offset. So, we have L larger than L prime. Now, this is an important observation. L must be larger than L prime. That is why L prime, L minus L prime, L minus L prime is E, the offset. Now, this allows us to extend the Grashof criterion for 4R through to 3R1P. This is what we are going to see now. So, as I have mentioned, two link lengths are infinite, but the difference is finite, which is known as the offset. So, remember that the offset is being measured perpendicular, the offset is being measured perpendicular to the direction of travel. So, this is the direction of travel of the slider, and offset is being measured perpendicular to the direction of travel. So, these are offset is the distance, perpendicular distance between the ground hinge and, in this particular case, the ground hinge here and the slider hinge measured perpendicular to the direction of travel. I can define distances between the ground hinge here and the slider hinge in various ways. I can join them and measure a distance, but this distance, please note, is measured perpendicular to the direction of travel, the distance between the ground hinge here and the sliding hinge on the slider. So, measured perpendicular to the direction of travel. So, we come to the Grashof criterion for 3R1P chain. Here I have redrawn the chain in a slightly different manner. Now, you can see this. Once again, the definition of E. Here I have purposefully drawn them as 90°, but they can be connected in arbitrary manner. So, the direction of travel of the slider is this. So, therefore, this is the sliding hinge on the hinge on the slider, and this is the other hinge. So, the perpendicular distance between them perpendicular to the direction of sliding is the offset. Okay. So, with this explanation, let us now move forward. What was Grashof criterion for 4R chain? Just let me recollect. So, L min plus L max less than equal to sum of the other two links. This was Grashof criterion for a 4R chain. Now, we have seen that L max is infinity in a 3R1P chain. The longest link is infinity, that we had written as L. There is another infinity. So, let us choose. Let us say this is also infinity. So, this was L prime, if you remember from the previous slide. So, L max was infinity, which we indicated by L, and there is another infinity, let us say P, that is indicated by L prime. Now, L minus L prime is E, that is how offset is defined. So, therefore, if I bring this P onto this side, what I get for a 3R1P chain is L min plus L max minus P is E, and that must be less than equal to the other link. So, this is what it is. This is what Grashof criterion for a 3R1P chain is. Let us look at it formally. So, if L min is the length of the shortest link, E is the offset, as I have mentioned, I have defined this distance perpendicular to sliding direction between the two hinges on the P pair links. So, if this is one of the sliders, this is another slider. So, slider 1 and slider 2, link 1, these two links, the slider is a link and this is a link. I call them S1 and S2. So, the hinge on S1 is this, while the hinge on S2 is this. So, in another way I can define offset as the distance perpendicular to the sliding direction, this is the sliding direction, distance perpendicular to the sliding direction between these two hinges. One hinge belongs to slider 1, the other hinge belongs to slider 2, both are sliders with respect to one another. If something slides with respect to another, the second one slides with respect to the first. So, both are sliders and these are the hinges on the two sliders. So, that is offset again, and let us say P is the length of the other link, then Grashof criterion says for a 3R1P chain states that if L min plus E is less than equal to the other link which is P here, then the shortest link can rotate completely with respect to all other links. So, that is Grashof criterion for 3R1P chain. And we call this a Grashof 3R1P chain if it satisfies this Grashof criterion. Now, let us look at inversions of the Grashof 3R1P chain. If I fix this slider, as I have been mentioning that there are one is this slider block, the other is this the slider block, and this link is also in sliding with respect to that slider block. So, there are both sliders. So, if I fix this link as ground and if it satisfies the Grashof criterion, then L min can rotate completely. And relative motion between any other pair of links, maybe this slider and this slider, or this slider and this link, they are all in oscillatory motion. So, therefore, this slider block can only slide, oscillate, the sliding motion will be oscillatory between certain limits. Of course, this needs to be extended. So, when L min rotates completely, all other links are in relative oscillation. So, this slider block will slide. This is called therefore a slider crank mechanism. So, this is the crank. And this is the slider. So, slider crank mechanism. Now, this has distinct assembly modes. Now, how do we understand the assembly modes? So, let me draw. So, this is a slider sliding on the ground. So, this is the ground. So, this is one extreme configuration of the slider, this is another extreme configuration of the slider. So, the slider oscillates between these two configurations. Now, I can also assemble the mechanism like this. I can put the slider on this side and assemble the mechanism. In that case, it might oscillate between these two limits. Now, it cannot go from this assembly configurations to this assembly configurations. This cannot go. As you can see, the slider can only oscillate between these two. Here it can oscillate between these two. So, there are two distinct assembly modes of a Grashof chain, as we have seen before also for a 4-arc chain. The slider cannot cross over from one to the other. Now, if I fix the shortest link, which we have seen, the shortest link can rotate completely with respect to other links. So, if I fix the shortest link, all links should be able to rotate completely with respect to the shortest link. So, this can rotate completely, this can also rotate completely. But the motion between these two sliders, so it has got sliding motion, that will remain sliding. So, this is called an inverted slider crank mechanism. Inverted slider crank mechanism. If I fix this link P, so this is the situation that this can rotate completely with respect to. So, P is the ground. So, L min can rotate completely with respect to the ground. Now, this is also an inverted slider crank mechanism. The thing is, you should note that here this sliding direction can rotate because of this hinge on the ground. The slider can rotate. The slider can rotate with respect to the ground. I mean, it will of course oscillate, but the direction of sliding is changing. If you see here, here also the direction of sliding is changing because this link is rotating completely. So, the direction of sliding can change continuously. So, this here the slider can rotate completely. Here the sliding direction remains fixed because this link is fixed. So, sliding direction remains fixed. Here the sliding direction can rotate completely, here the sliding direction will oscillate, but the sliding direction will change, it can change. Now, if I fix the slider itself, the slider block, again the sliding direction becomes fixed. Now, this becomes a slider rocker mechanism. It is the L min which can rotate completely. You see, the L min can rotate completely, but others only oscillate. So, this is translational motion, translational oscillatory motion, this is rotational oscillatory motion. This is a slider rocker. So, this is the rocker, and this is the slider. So, let us look at non-Grashof 3R1P chain. So, if L min plus E is greater than P, then each link oscillates with respect to the others. So, Grashof criteria is not satisfied, means this must be the condition for a non-Grashof 3R1P chain. All inversions of a slider rocker of this 3R1P non-Grashof 3R1P chain are slider rocker mechanisms. All inversions of the non-Grashof 3R1P chain are slider rocker mechanisms. There is a single assembly mode, as we have seen before. Now, let us look at the RRPP chain. Now, when we go from 4R to 3R1P, so 4R to 3R1P metamorphosis that we have discussed, there were two link lengths which were infinity. Two link lengths were infinity. Now, when we introduce another slider like we have done here, it is RRPP. So, we are having three link lengths as infinity. There are three link lengths that are infinite in an RRPP chain. So, what do you expect? L min plus infinity. Now, this has to be less than or equal to the other two infinities, sum of other two infinities. So, therefore, an RRPP chain is always Grashofian, because it satisfies this Grashof criterion. It satisfies the Grashof criterion always. So, this is always a Grashof chain. Let us look at an application. We have seen this application before, the Oldham's coupling. Let me quickly tell you, this is one shaft, this is the other shaft, both can rotate completely. So, this is here, this is connected to the other shaft, and the coupler is this, the middle piece. So, this can rotate completely, both shafts can rotate completely. Had it been non-Grashof, obviously it would be useless. So, three link lengths are infinite, Grashof criterion is always satisfied, and the smallest link can rotate completely. Now, if I fix the smallest link as I have done here, I have fixed the smallest link, therefore, all links should be able to rotate completely with respect to the ground link. So, all of them can rotate completely. That is why you can connect two shafts. All of them can rotate completely. Now, RPRP chain is always non-Grashof. Now, you can guess, you have 4 link lengths as infinity here. It is in such a way, the p's have been replaced in such a way that 4 link lengths go to infinity. So, this never satisfies the Grashof criterion, and one of the applications we have seen before, the Davis steering wheel mechanism. So, 4 link lengths are infinite. Whenever we say 4 link lengths are infinite, always this is in reference to a 4R chain. Always remember, this is in reference to a 4R chain. So, with reference to a 4R chain, we say that these are all 4 link lengths are infinite. Grashof criterion is not satisfied, all links have relative oscillatory motion. So, let me summarize. We began with the metamorphosis of a 4R to a 3R 1P chain, then we extended the Grashof criterion for the 4R chain to the other chains, and we have looked at the inversions and assembly modes of these various chains. With that, I will close the lecture now.